Hello, my name's Mike Wooldridge. I'm a human studying artificial intelligence.
Hello, I'm Ada, the artist robot, and I create art that helps people consider the future.
The robot Ada is painting my portrait, but this process takes a while, so we started a few minutes ago. We're going to come back at the end of the lecture and see what Ada's managed to do. Ada, can I go now?
Yes.
Thank you. Hello and welcome to the first of the 3 Royal Institution Christmas Lectures, an event supported by CGI, in which we'll see what artificial intelligence is, how it works, and how it's shaping our world. We're entering an era where intelligent machines can do things that seemed impossible just a few years ago. And the pace of change of this new AI is surprising even the scientists that built it. And this new AI was made possible by artificial neural networks inspired by the structure of the brain. And our story starts with this. This is a human brain. Of all the wonders in the universe, this is the greatest. Forget about black holes and neutron stars and supernovas. You are looking at the most incredible thing in all of creation. All of human experience has its origins here. Every thought, every dream, every hope, every love, everything it means to be human, from Shakespeare to Taylor Swift, all has its origins here. It is the ultimate triumph of evolution. It's a marvel that we are still nowhere close to properly understanding. And human brains like this one and like yours are unimaginably complex. They have huge numbers of cells that are connected to one another in enormous networks. And those cells are called neurons. We estimate that a typical brain, a typical human brain like yours or this, has about 86 billion of them. And neurons are the basic building blocks of human intelligence. Somehow everything that we are emerges from what they do and the way that they interact with each other. So it almost seems like heresy to suggest that we can build a machine which does something like this incredible organ does. But that is the dream of artificial intelligence. But can we really recreate human intelligence with this? This is an intelligence processing unit, an IPU. This is a bit like one of the processors in your home computer, but it's designed to process enormous amounts of data in parallel, and it turns out that is perfect for artificial intelligence. Now, IPUs like this are not brains. They don't have neurons, but they are built from huge numbers of very simple computational devices, transistors. This IPU, this state-of-the-art IPU, has about 60 billion transistors. Remember, compare that to the something like 86 billion neurons in the brain. It doesn't sound that different. So how far are we from using IPUs to recreate something like human intelligence? Before we go much further, we thought we'd show you an example of the kind of incredible thing that artificial intelligence is capable of today. For this, please welcome our first guest, Sarah de Lagarde. Hello, Sarah, and welcome. Welcome to the Christmas Lectures. Now, Sarah, you have a truly remarkable story. Will you share that with us?
Yes, of course. So, just about 12 months ago, I was in a terrible train accident, and as a result, I lost my right leg below the knee, and I lost my arm above the elbow.
Oh, wow. And so you've been fitted with a prosthetic arm. Those are nothing new, but what makes this one special?
So this one's pretty special because this is what we call a bionic arm, and it's powered by artificial intelligence.
OK, now I understand at this point you've got a party trick to show us involving a can, is that right?
Yes. Well, the first thing I wanted to show you is that I've got a movable wrist that can turn all the way round. And then it's got a little bit of power as well. So let me try to crush this can for you. Oh, oh, oh.
OK.
It does work.
That really is quite a party trick. So how does your arm know how to do that?
Well, basically, the way it works is that I think about the movement that I want to make, and I twitch a series of muscles, and the muscle twitches are being recorded by 16 electrodes that are positioned inside the socket, and then transform that into electric impulses that run through the forearm and powers the Covey hand, my bionic hand.
OK, and where exactly does the AI come into the picture?
So the AI is a lot of data recording. It's basically every time I use the arm, every time I make a movement, it records it. It starts to learn how I use the arm, and it starts to predict the movements that I want to make, including rotating it like that.
I could watch that all night. OK, so the AI is being trained on your body, but is your body and your brain, are they adapting to the AI?
So I did have a lot of training to understand, because it's very different to think about a movement, and it's more difficult to control it when it is bionic. But when I take the arm off at night and I recharge it like an iPhone, then I miss it.
How would your life have been like without this arm?
Well, I have to say that this world is being designed for people with two hands, everything. Think about the zipper on your coat, for example, or on your bag, on your rucksack. Think about a parcel, a packaging. For everything, you need to have two hands, one to hold it down and the other one to rip off the lid on something. And with the arm, it helps.
OK. Now, this technology is evolving. AI is moving very fast. What do you hope this arm is going to be able to do in the future?
So I really hope that this is going to evolve, become even more performant, because the idea is that at the moment it takes me about 10 seconds to think about a movement and then execute it. That's the AI part that hopefully will reduce that time and become instantaneous, like my other hand.
So as the AI gets better and better, that's going to help you in your life?
And I really dream that one day I can go back to riding a bike, and if I'm lucky, maybe I can drive a car again.
Sarah, that is a truly remarkable story. Thank you so much for sharing it with us. Thank you, Sarah. So AI is already capable of amazing things, and it's helping Sarah every day. And in this example, it's working with Sarah's body. But as AI gets better and better, some wonder, might it eventually be able to think like a human? Now, this is a question which has been with us ever since the origin of the first computers. And the best known answer to that question was provided by this man. This is Alan Turing. You may have heard of Turing through his code-breaking work for the Allies in World War II. But Turing was also one of the inventors of computing and one of the inventors of artificial intelligence. And a test that he invented has become one of the best-known ideas in AI. Turing's test is a beautifully simple and elegant way in which we can test machines for intelligence. And we're going to carry out a live Turing test now. I need a volunteer. Hands up to be a volunteer. OK, you in the hat there. Come on down. OK? Come and stand here. Hello, what's your name?
Xanthi.
Xanthi. OK, thanks for joining us, Xanthi. We are going to test you to see if you are a human being. OK, that's nothing to be alarmed at. The team are going to take you backstage. We're going to see you shortly. Just follow their instructions. Thank you, Xanthi. So Turing suggested that if a human judge is unable to tell the difference between a human and a machine by just having a conversation with them, asking them questions and looking at the answers, then we should assume that the machine has human-like intelligence, because we can't tell the difference. And if we can't tell the difference, Turing said, then it's redundant to argue about whether the machine is really intelligent, because we can't tell the difference. And with Xanthi, we're going to run a live Turing test. Now, behind us, we have two boxes, box A and box B. One of those two boxes has our volunteer Xanthi, and the other holds a computer. Now, the computer is running some advanced artificial intelligence, something like ChatGPT. And we've asked that artificial intelligence to respond to questions in the way that a human teenager would. Now, we asked all of you in advance to send in some questions, and we had a look through those and selected what we thought were the most interesting of those questions. They're in this hat right now. And what I'm going to do is I'm going to give you the hat. You are going to be our questionnaire. When I ask you for a question, I want you to stir up and give me one of those questions. OK, so first, questionnaire. OK, and the first question is number 2, Noah. Noah, where are you? Here you are, Noah. OK, take the microphone, Noah, and then tell us your question.
What is your favourite memory from when you were a child?
OK, so, human, artificial intelligence, what is your favourite memory from when you were a child? Go. OK, we've got our answers. Let's get the answer from box B first. Christmas mornings, always magical and fun. OK, and let's get the answer from box A. My favourite memory probably is when I was 4 or 5 and I would play in the park with my best friend and brother. He actually goes to the Royal Institution. OK, good answers from both. Let's get another question. Stir the hat. OK, let's have one of the questions. Thank you very much. OK, this is question 11 from Oliver. Oliver, where are you? Oliver, up there. OK. Oliver, read your question.
What was the best present you got on your last birthday?
What was the best present you got on your last birthday? Pass the microphone back. OK, human, artificial intelligence. What was the best present you got on your last birthday? Go. OK, box A, give us your answer, please. The best present I got was probably art supplies. OK, and box B, a new phone, totally loved it. Who doesn't love a new phone? So, questionnaire, mix them up again. OK, let's get one of these. And this is from Tomohiro. What was your question, please? Into the microphone.
What are your dreams for the future and how do you plan on achieving them?
OK, human, computer, what are your dreams for the future and how do you plan on achieving them? Go. OK, we've got our answers. We're going to go to box B first. Box B. Achieve success, happiness, work hard, stay positive. This is pretty good advice for life, folks. You can take that away with you for free. Box A. In the future, I plan to live in a cabin in Norway and be a successful environmental lawyer with my cat. OK, we're done with our questions. Now, you are the judges. You have to decide which is the human. That's what we're asking you. If you think the human is in box A, put your hand up now, OK? OK, that's quite a lot of you think the human is in box A. I'm looking up into the stalls. There's quite a lot there. If you think the human is in box B, put your hand up now. OK, there's a couple of people. I'm getting only a couple of hands. So I think the overwhelming majority of you think the human is in box A, right? Well, let's take a look. Let's see what's in box A. And it's Xanthi! Xanthi, that was an incredible set of answers. You've completely convinced the audience. There was no doubt here about where they thought the human being was. Were you pretending to be a robot, or were you just being Xanthi?
So I was basically just being honest, yeah.
OK. Well, you are the only person in the whole room that's been certified as human, and overwhelmingly certified as human. Thank you, Xanthi. You've been a star. So we're going to take a look before box B goes. We're going to take a look and see what's inside box B. And box B is our advanced artificial intelligence. Well done to all of you who guessed correctly. Well done. Important though it is, most AI scientists today don't think that the Turing test is the end of the story for artificial intelligence. Even advanced AI can't necessarily pass the Turing test today. Turing's test only looks at language, and as we saw earlier with Sarah, you can do infinitely more with AI than just have a conversation with it. But the surprising thing is that some things that we find really hard as human beings turn out to be really easy for AI, and some things that are very hard for AI are incredibly easy for us. So we're going to have a little illustration of this. We're going to play the Can AI Do It game, and I need a volunteer. So let's have some hands up, some volunteers. Okay, you, come on down. Stand here. What's your name? Naranjin. Okay, thank you very much for joining us. Now, we're going to play a little game, and I'm going to ask you to look at the screen. And what's going to happen is I'm going to show you some tasks that we might want AI to do for us, and I just want you to tell us whether you think AI can actually do them or not. Okay, is that clear? Yeah? Okay, so let's start with a maths problem. Okay, folks, look at this. Hands up if you think you can do this in the audience. Anybody? Couple of moderately, oh yes, some very confident people up here. What about you? Do you think you can do that one?
I can't do that.
You can't do that one. Okay, so turn around, face the audience. So do you think that AI can solve that equation?
Yeah.
You think AI can solve that equation? Okay, well, you're absolutely right. AI can solve it quite easily, and this, as it turns out, is the answer. Folks, you can check that when you get home. You can do, that's your homework for tonight. So most people, I think most of you in the audience, find maths problems like that really quite hard. Now let's look at a problem that's a lot closer to home. Okay, what's this? This is a messy bedroom. Is that your bedroom?
No.
No, well, I'm very glad to hear it, but actually that's AI-produced image of a messy bedroom. So, do you get asked to tidy up your bedroom?
Yeah.
Yeah, we all get asked to, I get asked to tidy up my bedroom. I'm nearly 60 years old. Okay, so, do you think we have AI today that could go into that room and tidy it up?
No.
No, you don't? Okay, does anybody think we have AI today that can do that? A couple of people that can do it? Well, no. Sorry, parents, but I'm afraid AI can't help you with messy teenage bedrooms. They're a tricky problem for AI to solve. But isn't that weird? You all looked at that equation and thought, wow, that looks really hard. But looking at a messy bedroom, do you think it requires intelligence to tidy up a bedroom?
Little bit.
A little bit of intelligence. But you don't have to be a genius. You don't have to be Einstein, do you, to tidy up a bedroom? No, you just have to want to do it, don't you? Okay, all right, so the really interesting thing then is some things that we find easy are really hard for computers, and some things that are really easy for computers are really, really hard for us. Okay, thank you so much, and, well, do you want to clear up your mess?
Can I take the football?
Take the football. The football is yours. We've learned an important lesson about AI. Lots of the things that we can do, things which we often take for granted, are far beyond the reach of today's AI. And yet today's AI can easily do things that most of us think are phenomenally hard. The capabilities of AI today, as we saw with Sarah, are incredible, but there is no AI at present that can do everything which you all can do. But what we know for sure is that the way that both human and AI process our questions and come up with answers can be compared, just like we did in the Turing test. Now, if we want to build an intelligent machine, then maybe it's useful to look at the one example that we actually have of intelligence in the world today. Us, human beings. And in fact, the most successful approaches to contemporary AI were indeed inspired by the structure of brains. This is the idea at the heart of contemporary AI. Basically, all the progress that we've seen in AI this century is because artificial neural networks have started to work on problems that are big enough to be really, really useful. So to understand AI, perhaps it's going to help to know a little bit more about what's inside our heads. Now, for this next part, I'm going to show you how neurons fire, and to do this, I need the help of the Royal Institution's very own neuroscientist, Dr. Daniel Glaser and Dr. Arjuna Nagendran. Daniel, we're talking about neurons. Did you happen to bring a neuron with you?
I did bring a neuron, Mike. Neuron is just a nerve cell, and it's a cell that produces electrical signals. This neuron I've brought is in my spine, and it's connected to the muscle in my arm. It gets signals from my brain, and what we're doing here is we're going to listen in to the neural signals from my brain from a nerve in my arm. We're using an electrode, which Dr. Arjuna is going to put in, which doesn't hurt at all, I'm told.
OK, Arjuna, can you tell us a little bit about what you use this equipment for?
Yeah, so EMG, or electromyography, is used to give us an insight into nerve and muscle function, and also when things go wrong.
So, let's get this ready.
Okay. So, Daniel, just relax the arm.
So that sound you can hear is a few spikes from the neuron in my arm. It's being controlled by my brain. And if I start to straighten my arm a little bit more, you get more spikes. And that's because neurons either fire or they don't. They don't have strength, they just have number of pulses. If I try really hard, you get loads and loads of spikes. So that's a neuron right there, Mike. It's a device that either fires or it doesn't, and it fired loads of times when I was trying hard.
OK, and those little clicks, they're basically the sounds of neurons firing.
They're sending pulses down their axon wire to show that they're excited.
OK. Thank you, Daniel. Thank you, Arjuna. So now we know what neurons are. They are cells that relay electrical signals in our brains, just like the brain we saw earlier, but also in our bodies, as we saw in the demo there with Daniel. But what we're now going to see is what happens when you put a bunch of neurons together. OK.
So this is a microscope, Mike, and George is going to turn it on. We've got a dish, if you can pass me one of those there, which is inside it, and in it are human neurons. Now, we haven't got them from grown-up people. We've grown them in a lab. We've reprogrammed their DNA using AI, Mike, and they've grown in this dish. And because they're neurons, what they've done is they've connected themselves up into networks. They are firing all on their own, and if we look at the screen over here, Mike, we should be able to see these neurons firing. So those green dots that you can see are human neurons that have grown in the dish. And if you look very carefully, you can see little glimmers as they send signals to each other. Yep, did you see that firing there? And the electrical pulse there. These are just neurons in a dish, but they can't help themselves. They've connected themselves up together and they're firing.
OK. So what we've got is these neurons, each of these green dots is a neuron. They're connected in networks and they're sending signals to one another, just like we saw in your muscles. That's really beautiful demo. Fouad from BitBio, thank you so much for joining us. George from King's College, thank you so much for joining us. Thank you, Daniel. Now, all of the many billions of neurons in our brains are firing just like we saw those fluorescent neurons in the Petri dish firing. But what is each individual neuron actually doing, and how do they come together to create intelligence? How can they make decisions? To explain, please welcome scientist Steve Mould. OK, Steve, what on earth is this contraption that we're looking at here?
So this is a really simple representation of a neural network. This particular neural network can identify pictures of mammoths.
OK.
Sounds impossible.
It does sound a bit impossible.
But hopefully we'll get it working. We need the help of a volunteer, though.
OK. In the yellow cardigan there. This one there. OK, what's your name?
Rahel.
Hello, well, welcome. OK, Steve.
So I'm going to show you a picture. I'll reveal it to you. No one else is going to see it. It's going to be one of the images on the screen here. I'll just quickly reveal it to you. You ready? OK, you take that. So I need to think about two things. how hairy was the animal in the picture and how big was the animal in the picture. I want you to think about those things in terms of like a scale of 1 to 10 while I explain what's going on over here, okay? So we've got these two containers that we can pour water into through these funnels. You can think of these like neurons. So this needs to be able to identify if something is hairy or not. This needs to be able to identify whether an animal is big or not. We'll start with hairiness. Question 1, on a scale of 1 to 10, how hairy was the animal in the picture I showed you?
I think about an 8.
About an 8, okay. So we've got all these beakers of water here that they're labelled 1 to 10, and you can see the amount of water goes up as the number goes up. So you chose 8, right? There we go. So that's quite a lot of water. So take that, and I want you to pour that into the funnel. Can you reach that? Yeah, just about. Okay, great. Yeah, keep going. That's fantastic. So because you chose quite a lot of water, the level should be able to rise to at least this funny little U-bend here. I want you to watch what happens when it gets there. Look at that. So that channel has now turned into a siphon, and that siphon effect is pulling all of the water out of this neuron and dumping it in this one. So you chose enough water to reach the activation level of this neuron. So this neuron activated, it fired, and it sent a signal to this neuron here. But you'll notice, look, this neuron hasn't activated yet. That's because the activation level is higher. It's up here. So this neuron is only going to fire if it gets a signal from this one and this one at the same time. So question number 2 then. On a scale of 1 to 10, how big was the animal that I showed you?
I'd say about a 9.
A 9, okay. So this is beaker number 9. So come around here, and you're going to pour in to the second container, the second neuron. And again, hopefully it's enough. It's quite a lot of water, quite a big number that you chose. That's going to automatically prime the siphon again. There we go. So now this neuron is getting a signal from both of them, and hopefully it's going to reach the activation level. And there it goes. So this neuron is now firing, and it's sending a signal this time to, this is basically our readout. So you can see the needle is swinging away from not mammoth and towards mammoth, right? So that's, and by the way, it is very slow. Like a real neuron, it's basically instantaneous compared to this. But the question is, did this incredibly sophisticated neural network get the answer right?
Well, this is what Rahul was showing. Success! It's a mammoth. Okay. That very simple neural network there, just with those a couple of neurons, was able to do a simple pattern recognition task, a simple decision. Now, ChatGPT does not involve buckets of water at all, but nevertheless, you can start to see how neural networks like this can make simple decisions and be able to put together, can do complex problems. Okay, thank you very much, Rahul, and thank you very much, Steve. Thank you. Now, we wouldn't be able to build a physical network with buckets of water that can represent all the tens of billions of neurons that are in our brain. They make literally trillions of connections. We couldn't connect together with pipes like that. But this century, we've been able to use the power of modern computers to build networks like this using software. And these are artificial neural networks. And they contain billions of neurons arranged into layers with those software neurons communicating just like we saw in the Petri dish, but also just like we saw in Steve's experiment. So how do we design neural networks out of software to be able to recognize a face or to play a game? The simplest way that we do this is with what's called supervised learning. And supervised learning works by us labeling things for the computer so that it's able to learn and recognize them on its own. We train AI like this every day. Whenever you upload a picture of yourself or your friends onto social media and you label it with your name or their name, what you're doing is you're providing training data for the AI of the social media company so that it will be able to recognize you and your friends in the future. To build AI that can do things for us, it needs data. Without data, we wouldn't have the powerful AI systems that we have today. And data about people about you and me is a really precious commodity for the companies that want to build AI. But as well as supervised learning, there's another way that AI learns. And to demonstrate it, I need the help of machine learning scientist Safa Abbas. Welcome, Safa. So tell us a little bit about your job, what you do.
So I help companies apply AI to their business by implementing machine learning solutions to understand and analyze data and make predictions and just help their day-to-day workflow. So depending on the data that our clients give us, we can use supervised or unsupervised learning. So when we have labeled data, we use supervised learning. But sometimes we have data that isn't labeled and not structured, and that's where we use unsupervised learning to discover patterns within the data for itself.
Okay, well, we're going to have another demo. We're going to play another game. We need a volunteer. Come on, put your hands up. Okay, I'm going to take you, please. Yeah, please come on down. Hello and welcome. What's your name?
Khadija.
So you go in the middle. So, Safa.
Yes, so this conveyor belt is going to bring out a bunch of objects that are going to represent our data set. And what I need you to do is to organize them into 3 categories. But you can choose to do it however you like. You have about 15 seconds for this task. So if we just let the objects come out.
You just organize them how you think they're best organized. Okay, I see where you're going with that.
Great. Khadija, do you want to tell me a little bit about how you decided to categorize your objects?
I was thinking about the ways they can go, and I had 2 solutions on how it can go. One of the ways which I done was do knife, fork, and spoon. But another way I could have done it was by the object. Like it could have been the metal, or it could have been the plastic and the wood.
Oh wow!
Yeah, you're
That's
thinking
great.
very fast, I
very
have to
fast.
say. This is very impressive. Safa.
Okay, great. So now what we're going to do is complicate the task a little bit by bringing out some more objects. So we're making our data set bigger, and I want you to do the same thing.
Over to you.
No time limit on this one because there's a lot more objects for you to look at. Great. Okay, thank you, Khadija. So do you want to tell me again how you decided to categorize these?
This one was more complicated, but I decided to think a bit more outside the box. This one is for metals. This one is with wood and plastic, and this is the ones that I could not categorize.
Okay, great. Thank you so much. So this is a really, really simple way of demonstrating how unsupervised learning works. So Khadija here kind of represents our algorithm that is observing the data and learning patterns within the data and then categorizing it. Yeah? Okay, so there's one more thing to do. We've got a random object, and we're just going to test our algorithm as it's been trained. And just this random object, where would you put it? Okay, great. So it fit into your kind of other not wood, not metal category. Okay, great. Thank you so much.
Okay. Thank you, volunteer. You're wonderful, and you were thinking very quickly on your feet there. Okay, Safa, so when is unsupervised learning? I mean, we saw that if you could label data, you can do really quite powerful things. So when do we need unsupervised learning?
Yeah, exactly how you said. So supervised learning, we need kind of a ground truth. We need, when we train, the algorithm will learn what's right and wrong from the data, but we don't always have that. In the case of this data set where we kind of had no rules, we didn't know which way to categorize it, the algorithm can learn to find the best pattern. And sometimes we work with really, really large data sets that are difficult for us as humans to label, and also difficult for us to recognize patterns in. So yeah, this is where we kind of use unsupervised learning, where we want to understand our data without obviously knowing what we're working with.
Okay. Thank you so much for joining us, Safa, and making a difficult subject very comprehensible. So with both unsupervised and supervised learning, in fact, with any sort of neural network, scale matters. The size of the neural networks, the number of elements it contains, the number of neurons and the number of connections between those, the amount of computer power that you can use to train the model, and how much training data you have to build it, these are all the key ingredients of AI. But as we've already seen, the more data you train a neural network with, the better your results are likely to be, and nowhere is that clearer than with large language models. A large language model is a model like ChatGPT or Cohere or Google Bard. It's a type of AI that can recognize, summarize, translate, and even completely create new knowledge. So, and the picture behind me is the Bodleian Library. This is from my university in Oxford. It's one of the oldest libraries in Europe, and it's what's called a copyright library. That means every time a new book is published, the Bodleian gets a copy of it. That's a lot of books every year. And in 1598, the Bodleian Library held about 2,500 books. Anybody read 2,500 books? That's a lot of books. Okay, now, we are going to try and visualize the amount of data that's used to train large language models like Cohere or ChatGPT or Bard. So, this tiny little sliver of confetti, which is so small that I think probably the people at the back can't even see it, and I'm having difficulty holding it, that is a representation of how much the Bodleian Library had in 1598. Okay? That is the amount of data that the Bodleian Library had in 1598. Well, today, the Bodleian Library is home to around about 13 million volumes. This is a picture of the Bodleian Library today. Has anybody read that many books? Okay, somebody thinks they have. I don't think you've read 13 million books. Okay, so that is represented by this amount of confetti. Remember, this, it's even disappeared. That tiny little sliver of confetti is the Bodleian Library in 1598. This is the Bodleian Library today. So now, on that scale, let's see how much confetti you would need to represent all the data that was used to train Google Bard. That's a lot of confetti. That's an awful lot of data. So how do large language models use all of this data, this unimaginable quantity of data, to be able to just make a sentence? To understand that, we're going to play a game, and this is called the prompt completion game. Okay, now, we've got two teams that are playing this, Team 1 over here and Team 2 over here. And all they're going to do, these two teams, is construct a sentence. And they're going to do that one word at a time. You, in column A, in column 1, as you pass the piece of paper down, you're going to write a word, but you only see the last word that was written down. So you're going to fold the paper over so that the person in front of you only sees the last word that was written. You, on this side, you're going to do the same thing, but we're not going to fold the paper, so you are going to see the whole of the sentence. And what we want you to do is just construct the best possible sentence that you can. Okay, ready? 3, 2, 1, go! Okay. The game that we're playing here illustrates the way that language models work. All they try to do is to predict the next word that comes after the words before it. You've already seen this idea when you send messages on your phone. If your mum starts to send you a text message on her smartphone, the phone will suggest completions for her. So, for example, if she types "have you," the phone might suggest "tidied your room" or "walked the dog." So the phone has learned that after she types "have you," that the likeliest next things for her to type are either "tidied your room" or "walked the dog." Here, your phone is doing just exactly what a large language model does. The difference is the scale, the unimaginable scale of data that these models are used to train on. Okay, we've finished. So let's come over here. Now remember, this is the column that did not get to see all the sentence before. They just got to see the last word. So let's see what genius you came up with. The boat sails fast. Car wash. Bomb explosion. Happening on an elephant. Your parents must be so proud, column 1. Let's see how column 2 did. OK. The cat is mean, and it paper cut on the table because of. OK, better, but guys, that's not Shakespeare, I'm afraid. I'm really sorry. I don't think we're going to be seeing any New York Times bestsellers from column 2. But nevertheless, they did a better job than column 1. Column 1's made no sense whatsoever. Sorry, column 1. It didn't make any sense whatsoever. But we set you up to fail there. There was no way that you were going to produce a sensible sentence if all you saw was the last word. Now, one of the reasons that large language models like ChatGPT and Bard and Cohere have started to work in the last few years is that they are designed to process whole sentences, not just one word at a time. And as we saw in our game, it's much easier to make a good guess about the words that come next if you see the whole of the sentence. And it sounds obvious, but the AI technology to make that happen was only invented in 2017. It's a neural network architecture called transformer architectures that was invented by Google. But OK, I've explained to you now how large language models like ChatGPT work. Do you think they understand what they're doing? I have to tell you, I don't. Large language models don't understand the meaning of the sentences that they are constructing. So how do they determine which words are most likely to come next in a sentence? To answer this, please welcome from Cohere, Serafina Goldfarb-Tarrant. Welcome to the Christmas lectures, Serafina. OK, Serafina, we're going to try and understand how text is understood by large language model.
Yeah, so I'm a research scientist and I train them, but before I start to train them, I have to take all of that confetti data and I have to segment it into units, which we call tokens. And then you have all of that data, and then the language model gets what the word is based on the context it appears in, and then you can take one of those words and you can plot it into a space.
That's what we're going to do now. So here on the floor, what we've got is a graph. A graph, just like you've seen in your maths lessons at school. It's got two axes. This is the x-axis, and this is the y-axis. And what we're going to see is how we can plot words on this graph. Now, for the next segment, we need some volunteers, but they're not really volunteers at all, I'm afraid, because we need 10 of them. And so, our 10 volunteers who are going to come down, please, now from the second row. This is your moment. Come on down. OK, volunteers, so stand in the graph. And now, number 10, just come and stand over here. Your moment in the sun will be in a few minutes' time. Put your animals on so we can see your animals. OK, we're going to play a game. You're going to stand inside the axes of this graph to see how you can be plotted. And what I want you to do is just this. I want you to stand close to animals that you are similar to, and as far away as possible from animals that you aren't similar to. Got it? So let's count them down. 3, 2, 1, go! OK, so how's that looking now, Serafina, do you think?
Yeah, so it looks like we have the cat, tiger, lion group over here, which is like feline-ish. The wolf, fox, dog group over here, so canine-ish. And then the donkey, zebra, horse group over here.
So, you've just arranged yourself by putting ideas that are similar close to one another in this graph. And each of you now has a coordinate in the graph, an x and y coordinate. That's an x and y coordinate, which is identifying our cat. This is the X and Y coordinate that's identifying our tiger. This for the lion. So Serafina, is this what large language models do?
Absolutely. So large language models cluster words together that are similar, just like you all have done, by representing those words or tokens as coordinates in space, just like a list of numbers, which we call a vector.
Okay, so now, this is your moment in the sun, number 10. You're going to be a very unusual kind of animal. Come forward. You are going to be a toaster. What did you do in the Christmas lectures? I was the toaster. Okay, so same rules for you, right? Stand close to things that you're similar to and as far away as possible from things that you are unlike. Off you go. Okay, so number 10. Again, we set you up to fail. A toaster isn't like a horse, it isn't like a tiger, it isn't like a lion, it isn't like any of these things. In order to be able to plot you, we would need more dimensions. We would need to add more dimensions to this graph in order for you to fit. Okay, thank you all volunteers, and in particular our toaster, number 10. Okay, now, humans like us struggle to think in more than 3 dimensions. But for large language models, we need many more than 3 dimensions. Is that right, Serafina?
Absolutely, yeah. So what we noticed in this is that 2 dimensions was clearly not enough, because since the vector coordinates measure how similar things are based on their meaning, like similar meanings are close by, you definitely need way more than 2, right? You can't separate all words based on similarity in just 2 dimensions. So in practice, we use a little over 1,000.
1,000
in the language
dimensions?
models I train.
Wow.
Yeah.
Okay, that's a lot of dimensions. Okay, so the language models can draw lots of correlations between those different words. Is that right? And what we noticed was that those words, those animals that were similar, had actually very similar coordinates. Is that right?
Yep.
Okay, so language models don't just work with words, do they? Right? They can work with sentences or documents.
Absolutely, yeah. And that's the big innovation that we've had recently. We've been able to extend to much longer context. So here's like a little example of just 2 types of sentences embedded with one of my language models. We've made it in 2 dimensions. This is in 1,000 dimensions, but my computer can't do that. So I've had to project it into 2.
Just the same way that we did with the kids and the animals, we've reduced that sentence down to an XY coordinate?
Exactly.
Okay.
Yeah, so here we have, please set an alarm at 6 a.m. And in the similar cluster, let's see, we have alarm time for 12 p.m.
Okay, and they're similar sentences.
Exactly, and everything in that cluster is kind of alarm focused. And then this cluster over on the other side of the coordinates is like, what and who was I emailed about last week? And maybe all new email messages. So this is almost like the XY coordinates are email versus alarm in this case, but it's embedding the whole sentence.
Okay. So large language models reduce text, sentences, documents down to these vectors, these lists of words, and we saw vectors with just 2 dimensions, but in practice they're using many, many more than that.
Exactly.
Serafina, thank you so much for coming on and explaining this to us. Neural networks that embed word in galaxies like that, plotting their relationships to one another, might also enable us to communicate in ways that we have never thought possible. And to explain, please could you give a warm welcome to the author of How to Speak Whale, Tom Mustill. Tom, welcome. But how exactly do we speak to whales?
Well, if you want to understand what whales are saying, first you've got to listen. Is the flame organ ready? Are you ready? Yeah. All right. Play the voice of the blue whale. Blue whales are the biggest animal on Earth, and they've got the loudest voice on Earth. But until recently, we thought they were totally silent. Their voices are below human hearing, so we've sped them up and put them through this big subwoofer so you can hear them And we've also put them through the series of Rubin's tubes, which, with the flames, allow you to look at the characteristics of their voices and see their waveforms. These sounds from underwater recordings in Monterey Bay in California. But play the second blue whale. So can you see the shapes or maybe some patterns in these lines of flames? These are very helpful for us. When we have spectrograms, when we make pictures of sound, we can find patterns in those pictures of sound. And AI tools are really useful here because it turns out with natural language processing systems and human language, when you plot all the different parts of a language, say with billions of examples into a giant galaxy, you can find hidden patterns in those plots. And AI tools can find these invisible patterns that we can't see, there's no chance that our brains or mind could perceive them, and it can link them to patterns between languages. And things like Google Translate can match the hidden patterns between different human languages and translate between them.
Okay, now you prepared a demo for this, Tom, right?
Yes.
And for all our demos, we need a volunteer. So let's have some hands up for a volunteer.
You guys are keen.
Okay.
Sitagina poto sami kasaki konoki siki alitamato sa puso sana ika debukeri sano kawa sota sita sukro sasono usiganiki kusemakawa buko basota papu papuka ome kana Mento kimaga sono ega bonito nani yuri gai da tomotara.
You are keen. Where do you want to go, Tom? Who do you want to pick?
You.
Yeah. Okay, come on down. Hello. What's your name?
Maya.
Maya. Welcome, Maya. Okay, Tom, over to you.
Okay, Maya, do you speak any other languages?
No.
Perfect. Neither do I, but Google Translate is here to help us. Now, on this piece of paper here is a sort of graph of language with the sort of x-axis there and the y-axis there, and kind of imagine that there are thousands of other axes, but we can't because our brains don't work like that. But the AIs can make giant galaxy maps of huge amounts of words, and they can plot their relationships to each other. And what we need to do is to identify a pattern in this zoomed-in part of the galaxy map of words in the English language. So I'm going to ask you to find Wales. In fact, I'm going to give you a pen. I'm going to ask you, can you please put a circle around Wales? Very good. R. Oh, that's the wrong R. Sorry, I should have been like, not like R, not like R like a pirate. More like R. Maybe that R. Sorry. Too many R's. Google Translate does make mistakes sometimes too. And amazing. Okay, so Wales, R, amazing. So ignoring this one, we're going to now take away the English language map and imagine we're going into a totally different map of a different language system. So this is Japanese. And the natural language processing systems, the pattern finders, if you find the pattern for whales are amazing in English and you look in the same places in the kind of galaxy cloud of Japanese, what do you get? And don't worry if your pronunciation's bad, because mine would be worse.
I don't know how to pronounce it.
Well, Kujira wa Subarashi. Are there any Japanese people here? Was that terrible? Yes, it was terrible. But would you like to say it in Japanese?
Kujira wa subarashii.
Exactly. Exactly what I said. So now let's try it with one last language, with German. So ignoring R again, could you try that?
Well,
Yes?
sind
Yes?
unglaublich.
Unglaublich. Wales sind unglaublich. Are there any German speakers here? Yes. Could you say that? Shout it out in German.
Okay. Wale sind unglaublich.
Okay, but that's how it works, essentially. That if you have enough examples of a language and you can make a giant galaxy and you can find the shapes of a certain phrase in them, you can match those shapes between language without even having a dictionary. And that is how Google Translate works. It doesn't have a dictionary and it doesn't even know it's dealing with a language.
Okay. Thank you very much. Thanks for joining us, and well done.
Well done. Well done. And what's really exciting is we also don't have dictionaries for other species.
Okay. But Tom, how important are large data sets for this?
They're absolutely crucial. The AIs need billions upon billions of examples of language for this to work. If you find the pattern, you can translate it between different languages, and we would like to try and apply this to other species, but we need to get big data sets for that too.
Well, for human languages like English, we have lots and lots and lots of data, as we saw earlier, but whales don't write books. Where are we going to get the data from?
We need to get it straight from the whale's mouth, and that is what we've begun to do.
I think you were going to show us some videos at this point.
Yes, this is really special. Nobody else has seen this video, I think, in the world before. This is fresh from the sea from Dominica. So these are sperm whales. What can you see on the top there amongst them? That's a family group of mothers, grandmothers, sisters, brothers.
That looks like a little baby whale.
That's exactly right. That is a newborn baby sperm whale calf. It's so young, it's just a few minutes old. It hasn't even learned to swim yet, and its family is lifting up to the surface so it can take its first breaths. But what else strikes you about that video?
Well, there was no sound.
There was no sound. So now, let's play the second sperm whale video. So this is from the same family group, and this is from Project SETI, who are studying these whales. So those clicks you can hear, that is the conversations of these whales. Project SETI not only is studying their lives and their behaviors, but they're recording the conversations so we can match what they're doing with what they're saying. In 1 year, they have doubled the entire data set for every single recording of sperm whales that we ever had before. And in a couple of years, with that information, they hope to do embeddings like this of sperm whale communication systems and try and use these AI tools to find patterns within them. And I don't know about you, but when I see a video of an animal, especially an underwater animal, I make wildlife films, I film them underwater, and I can hear them communicating at the same time. It changes how I feel about them. I think about them differently. And Project SETI just this week has released some early AI analysis. They think that whales have vowels. We can't hear them, we just hear clicks, but the AI tools have found in between those clicks vowels, which maybe indicate that they've got something like a language.
Wow. So where is this going? I mean, am I going to be able to understand what my dog is saying to me soon?
I mean, maybe. We just don't know. We've never listened to other animals enough before, but dogs and cats are some of the biggest data sets we have. Think of the internet. It's almost like it was built for cats. So that's one thing. And there's another thing I love when I go out for walks. There's an app you can have called Merlin on your phone. It's free. You turn it on, it just listens to all the birdsong around you, and the AI scrolls through all of the sounds and it identifies which species they might be. And I think the most exciting thing is that maybe when I make my next nature film, it might not just have underwater sound, but it might also have subtitles.
That's incredible. Thank you so much, Tom.
Thank you very much. Thank you.
Okay. Before we wrap up, let's take a look at what the robot Ada's been doing throughout this lecture. Ada, have you finished my portrait?
Nearly there.
Okay, and what do you think of it so far?
I'm quite pleased so far. I hope you like it.
I've never had a portrait painted before, Ada. Thank you. In this first lecture, we've gone under the hood of AI to find out how intelligent machines learn. In lecture 2, we're going to have a look at how AI is already being used all around us. We'll look at breakthroughs in computer games, in medicine, and even in art. And we're going to see how ubiquitous AI is in our everyday lives, even though we may not be aware of it. Thank you. AI is here now. Discover the different ways it may already be revolutionising your life in my exclusive interview. To watch, head to bbc.co.uk/RI and follow the links to the Open University.